The aurora is a beautiful optical phenomenon that has been observed for many centuries. Aurorae are found in both northern and southern poles, the aurora borealis and aurora australis, respectively. It appears as curtains, rays, spirals, or dynamic flickers. But how does this happen? Why do we see what we see? It begins with our sun. The sun's outermost layer, the corona, continually expands, ejecting plasma in all directions. The plasma mostly consists of energized electrons, protons, and alpha particles. This is solar wind. These highly charged particles make the trek all the way to Earth, where they experience an interaction. But with what? The magnetic field. It effectively blocks the majority of these particles and their trajectories are changed. Now they flow towards the poles. The particles make it through the upper atmosphere where they excite the atoms.
But not all particles can make it quite as far into the atmosphere as others. The depth they travel depends on the amount of energy they have. If they don't have very much energy, they tend to get stopped and give their energy to particles in the upper oxygen layer. So the oxygen atoms here gain a little extra energy. If they have more energy, they may even make it to the lower oxygen layer. Most particles from solar wind tend to have enough energy to make it to this layer. And if they have even more energy than that, which usually only happens when the solar wind is especially strong, they may make it as deep as the nitrogen layer. But what do these layers have to do with the colors we see in the aurora, though? If we look closely at the aurora, we can actually see that different colors tend to occur at different heights. These correspond to the different layers of the atmosphere. You may be wondering what the energy of the particles has to do with the colors output by the atoms, though. So let's take a closer look, beginning with an atom in the lower oxygen layer. The excited electron will be in a high energy excited state, but this electron won't want to stay there. So instead, what it will do is choose to give off that energy and return to its ground state. In doing this, it needs to release the energy in the form of light. High energy electrons have more energy to give off, so they'll release a color of light that carries more energy. In the case of oxygen, green. Now, if we look at the case of a low energy excited electron, one we would typically see in the upper oxygen layer, it has less energy to give off, but still more than in its ground state. So it will release that energy in a low energy light, such as red. And that's why we see the colors of aurorae in layers.
So just to recap, there are three things that we see affect aurora. First up is the energy of the incident solar radiation, because higher energy radiation is able to penetrate deeper, and as we've discussed, that's what gives us the layering in our aurorae. The planet's magnetic field also plays a large part in this, as it's able to direct all the incident radiation up to the poles, which both affects where they spawn and affects their creation as a whole. The concentration of elements in the atmosphere also plays a huge part in the observation of our aurorae. The reason for this is because different elements are able to release different colors of light when their electrons drop from excited states back into their ground level energy state. That's why on Earth specifically we have green on the bottoms of our aurorae, and we see layers of different colors and that approach red at the top, because the incident solar radiation, where the high energy radiation is able to penetrate deeper and yield colors from nitrogen's emission spectrum, whereas the lower energy electrons release light from the oxygen emission spectrum. Now that we have an understanding about the aurorae formations on Earth, why not take a leap and look at the aurorae formations on other planets in our solar system? First up, we have Mercury, and we know Mercury has no discernible aurora because of its lack of a sufficient atmosphere. Now Mars and Venus are both in the same boat, and neither of them can form aurorae because of their lack of a sufficient magnetic field. And since we started by talking about Earth's aurora, that's it for the terrestrial planets. Now on to our gas giants. Now if you took a closer look at our chart from earlier, you would see that most of our gas giants have a very similar atmospheric composition. That's why we see the aurorae of most of the gas giants are very similar. This was Science for Dummies by Dummies, and we hope that we helped you learn a lot about the aurorae that exist in our universe.